Hello, everyone. Good morning. Welcome to Compass Friday special seminar. This time will be 45 minutes. Our guest speaker will be Dr. Xiaozhui Zhou, who's also a personal friend of mine, and currently she's a postdoctoral investigator at Princeton University under the supervision of Professor Luke Dyke. And before joining Princeton, she obtained her Bachelor of Science from Nanking University of Information and Technology, and her Master of Science from the Second Institute of Oceanography, both ranked high tier in oceanography back in mainland China. And she got her PhD from University of Rhode Island last year under the supervision of Professor Tetsuhara. And now she's a postdoctoral investigator in Princeton studying bubbles. So in her spare time, she likes to hike, watch movies, and spend time with her cat. And today she'll give us a talk about surface wave impacts on air-sea momentum flux and upper ocean turbulence under tropical cyclone. So please go ahead, Xiaozhui, and take the stage.
Thank you, Payson, for the lovely introduction. So now I can share my screen, I think. And I can show my slides. Okay. Can you guys see my slides?
Yes.
Okay, thank you. And thank you everyone for having me today. And thank you, Payson, for the lovely introduction. And I'm going to introduce my PhD work, Effects of Surface Wave on the Wind Stress and Upper Ocean Response under Tropical Cyclone. This work is done with my PhD advisors, Dr. Tetsuhara, Isaac Guinness, and it's a collaboration with Professor Eric Casado, Professor Jun Xu, and Dr. Brendan Reckel. As we know, the evolution of a tropical cyclone is strongly affected by the supply of the heat from a warm surface to sea surface, and the strong tropical cyclone transfers strong momentum flux into the ocean. When the strong tropical cyclone wind enhances upper ocean vertical mixing, deeps the mixed layer depth, and cools the sea surface temperature (SST), the reduced SST then can decreases the heat flux to the atmosphere and weakens the storm. At the same time, we know that strong tropical cyclone can generate very strong surface waves. It is hypothesized that the upper ocean response is significantly modified by the surface waves. The resulting Langmuir turbulence then can enhance the vertical mixing. Therefore, it can influence the whole tropical cyclone forecasting system. So we really want to improve the accuracy of the tropical cyclone forecasting system. This is very important for people living in the coastal area, especially people living in Miami, as you guys. And so to do that, we really want to improve the upper ocean simulation under tropical cyclone, especially for the sea surface temperature. And we really, to make that happen, and we really want to firstly improve the momentum flux parameterization at the air-sea interface under tropical cyclones, because this is a key driver for the ocean simulation. And then we also want to improve the upper ocean turbulence parameterization in the upper ocean under tropical cyclone, because this can make a better upper ocean temperature simulation under tropical cyclones. So one major uncertainty contributing to the two questions we want to answer is the surface wave. So we explored the lump-breaking surface wave impact at the momentum flux into the ocean at the air-sea interface. And secondly, we also explored its impact in the upper ocean response to the tropical cyclones. So today I'm going to introduce two major topics here. The first one is with title, drag coefficient and sea state dependency on the tropical cyclones. And then we go to the ocean side, the impacts of the Langmuir turbulence on the upper ocean under tropical cyclones. So let's focus on the drag coefficient at air-sea interface under tropical cyclones first. As we know, the momentum transfer from the air to the ocean is usually equal to the wind stress, and the wind stress is commonly parameterized with the air density, drag coefficient, and wind speed at 10-meter height. At the same time, the drag coefficient is also parameterized as a function of 10-meter wind speed in the operational ocean model. There are two major assumptions here in this process. The drag coefficient is assumed independent of the sea states, and the wind stress direction is assumed as same as the wind speed direction. So here's a question. Is the wind speed at 10-meter height is good enough to describe the drag coefficient? The previous studies suggested that the answer is probably no. In this plot from Xu et al. 2017, they summarize the observed drag coefficient as a function of the wind speed at 10-meter height from different studies. But when the wind speed is stronger than 25 meters per second, as I'm showing here in this box, mostly it goes to tropical cyclone condition. The drag coefficient becomes very scattering from different studies. We assume that the large uncertainty is partially due to two factors. Firstly, there is very few observations under tropical cyclones. Secondly, the drag coefficient is more variable because the sea state is more variable in high wind condition. In the high wind condition, the sea state dependency is likely even more important due to the stronger surface waves. So we really want to estimate the drag coefficient under tropical cyclone condition and the sea state dependency. Based on the previous studies and concerns, we try to improve the estimation of the wind stress by combining available observations and numerical simulations of the upper ocean currents under tropical cyclones. Here I'm introducing the observation dataset in this study. Our observation dataset is from 13 EMAPEX floats under 5 tropical cyclones: Typhoon Maggie in 2010, Typhoon Fanabi in 2010, Hurricane Francis in 2004, Hurricane Gustav in 2008, and Hurricane Ike in 2008. This is a structure of an EMAPEX float, which can measure the current, temperature, and the salinity profile under tropical cyclones. We majorly focus on the wind-driven current dataset from Xu et al. 2017 and 2019 on our study. At the same time, in addition to the observations, we use the Modular Ocean and the Wave model, MOM6 and WAVEWATCH III, to conduct numerical experiments under the same 5 tropical cyclones. Here, this figure is showing the detailed trajectory of all 5 tropical cyclones, as we can see in our study. And because the numerical simulations require continuous wind field, so in our study, we use the base track database to generate the continuous wind field to force the Modular Ocean and Wave model for each tropical cyclone. The base track database provides 6 hourly storm parameters, such as the location of the eye of a storm, maximum wind, and radius of maximum wind. Here is an example of how the wind field looks like for each tropical cyclone. The color indicates the 10-meter wind speed, and the detailed trajectory of EMAPEX flows are shown as purple curves. Then we set up the Modular MOM6 and the WAVEWATCH III model with very high resolution in both horizontal and vertical directions. Our horizontal resolution can reach to 4 kilometers, and we have 2-meter resolution in the upper 15-meter depths. And the initial condition for our model is assumed to be homogenized and start from the calm ocean. And then the initial temperature and the salinity profile is average temperature and salinity profile from each EMAPEX float before tropical cyclone arrives. As I mentioned, we use both observational and simulated upper ocean current to estimate drag coefficient in our study. So to do that, we need to develop a new method to estimate drag coefficient from the ocean side. Here is the recipe. And to simulate the upper ocean current, we applied the wind forcing field I just explained with an initial estimate drag coefficient to force a Modular MOM6 and wave model. For the initial drag coefficient, we use an MPRO drag coefficient parameterization in GFDL hurricane model. This is a GFDL CD, we call it. And the Modular MOM6 WAVEWATCH III model then can solve the momentum equation under 5 tropical cyclones, as I'm showing here. Secondly, we vertically integrate the momentum equation for 100-meter depths to the sea surface to get the equation 2, the vertical integrated momentum equation, as I'm showing here. Those as we focus on the right-hand side of the equation 2, here those three terms on the right-hand side are small enough based on Stanford 2011 and Xu et al. 2017. So we can assume they are nearly 0. And then we can see the left-hand side of equation 2 is equal to the wind stress in the vertical integrated momentum equation. Then we also know that the first two linear terms on the left-hand side are usually the leading order to contribute to the wind stress. So we can calculate the first two linear terms from both observation dataset and model simulations to obtain the vector sigma on the third step, as I'm showing here. After we get the vertical integrated linear terms from the observation data set and the model simulations, the sigma of OBS and the sigma seen as I'm showing here, and we can calculate the magnitude and misalignment of sigma from model simulation and observation. If they agree well, that means the magnitude ratio MR equals to 1, and the misalignment between the wind speed direction and the estimate wind stress phi equal to 0. That means the initial drag coefficient is a perfect drag coefficient. That is the GFD hurricane drag. If this is not, we still can calculate it or estimate the drag coefficient by multiplying by the initial drag coefficient we applied and the magnitude ratio MR. And we also can calculate the aligned drag coefficient by introducing the misalignment between the wind speed direction and the estimated drag wind stress. So since the method I just introduced is based on up ocean current, we also think the surface wave can influence the up ocean response, the current. So we believe the surface wave will influence the drag coefficient. The major impacts from the surface waves can summarize as 3 parts. First one is the sea state dependent Langmuir turbulence. Second is the air-sea momentum flux budget due to the growing and decaying sea. And the third part is the wave current interaction, which includes the Langragian, convection, correlate Stokes, and the Stokes shear force. And then, based on our understanding, we conduct 4 experiments to include those wave impact as just showing in this table. Experiment A is a wind-driven case with implicit sea state-dependent Langmuir turbulence influence. Experiment B includes the explicit sea state-dependent Langmuir turbulence. And experiment C, it includes Langmuir turbulence and air-sea momentum flux budget. In experiment D, it includes all 3 wave impacts we just mentioned. Now we can see how the drag coefficient look like under those 5 tropical cyclones. This is the figure of our estimated drag coefficient CD y-axis against the wind speed U10 in the x-axis. Different symbols indicate different model simulation, as I just introduced before. The estimation is being averaged over 5 meters per second interval. And the vertical error bar is 95 confidence level. The black curve is the initial drag coefficient we applied to force the Copter Mom 6 WAVEWATCH III model, the GFD hurricane drag. It can clearly show that the estimated drag coefficient under those 5 tropical cyclones is around 0.002 to 0.003 when the wind speed is between 25 meters per second and 55 meters per second. And also, we can see the drag coefficient is weakly depending on the wind speed in the wind speed range in this figure, even though you may see the stronger drag coefficient estimation when the wind speed is larger than 45 meters per second. But we do not necessarily believe this is true because a large error bar in this wind beam. In addition to the traditional wind speed dependency, we also investigate the sea state dependency. In our study, we choose 4 parameters. Firstly, the phi misalignment between the wind and the wave, and the wave age, and the input wave age, which excludes the swell phenomena and the traditional wave steepness. This figure is showing the spatial distribution of all 4 wave parameters in a normalized coordinate. It is a normalized distance to the eye of each tropical cyclone, and the color in each panel indicates the magnitude of each wave parameters. For example, the panel A is showing the misalignment angle between the dominant wave direction and the wind direction. In the panel B, the color is the wave age. In panel C, the color is the input wave age. In panel D, the color is showing the wave steepness. As we can tell, the wave field has very significant spatial distribution. Large misalignment happens in the front left and far front right-hand side of tropical cyclone. And then the wave becomes much younger just after tropical cyclone passes. At the same time, it also becomes much steeper. We need to keep in mind that the wave parameters has very strong correlation with the wind speed. It is not easy to separate the dependency of wind speed and dependency of the wave parameters. As I mentioned, our drag coefficient estimation is weakly dependent on the wind speed, so we can do the mean average over all wind speed together as a black square, as shown in this figure, which has least error bar. In this figure, the y-axis is still the drag coefficient estimation. The x-axis is a misalignment between the wind direction and dominant wave direction. It clearly shows that the drag coefficient is significantly reduced, with a misalignment angle between the dominant wave direction and the wind direction is larger than 45 degrees. Besides of the misalignment between the wind and the wave, we also tested the traditional wave age dependency, as I'm showing here. This result is showing in this figure, which is very similar with previous slide. The y-axis is still the drag coefficient, and the x-axis is the wave age. It shows very weak decreasing trend with the wave age for the low wind condition, but it is still in the hurricane condition in the old sea. Then the weak trend disappears for the high wind condition in the young sea. And we can tell that the drag coefficient is not very sensitive to the wave age based on our data set. Besides of that, we also tested the traditional wave steepness dependency. As I'm showing here, the y-axis still the drag coefficient, the x-axis is the wave steepness. However, we didn't see clear dependency of the wave steepness within our dataset. So, based on our investigation, we found 3 key points. Firstly, the estimated drag coefficient over all 5 tropical cyclones is around 2 and 3 when the wind speed between 25 and 55 meters per second. And we still think the shape of the drag coefficient dependency on the wind speed is an open question. The wind dependency of drag coefficient is very weak based on our data set. The most important thing is that the drag coefficient is dependent on the misalignment between the wind and the wave direction, which is not sensitive to the wave age and the wave steepness, which is pretty new compared to the previous parameterization. And you can see more detail in the published paper. So after we understand more about the momentum flux at the boundary layer at air-sea interaction under those 5 tropical cyclones, let's have a deep breath and dive into the ocean part. Just take a look at the impacts of surface wave on the upper ocean response under those 5 tropical cyclones. In this part, we still use the same 5 tropical cyclone condition, but introducing another interesting observation data set. In this part, we also combine the observation dataset and the numerical simulation together, in addition to the EMIPEX float observation. We also use observations from 11 Lagrangian floats under 5 tropical cyclones. Those 11 Lagrangian floats, which are deployed with the same with the EMIPEX floats. This figure is showing the structure of mixed layer Lagrangian float. They provide the vertical velocity variance observations through pressure measurements under those 5 tropical cyclones. It means it measures how strong the upper ocean turbulence it is under 5 tropical cyclones. And all observational data sets are also provided by Professor Eric Diazaro. We also use the identical wind field as we just introduced in the first part for the drag coefficient estimation. Since the WAVEWATCH III transfer the stock drift to the ocean model MOM6, here the bottom panels shows the surface stock drift under each tropical cyclone. The float trajectory are also shown as purple curves. Another very important key is projected Langmuir number for the Langmuir turbulence, which directly control how strong the Langmuir turbulence it is under 5 tropical cyclones. It is defined as the square root of the ratio of the frictional velocity to the stock drift average over the surface layer, which is upper 20% of the mixing layer. It is also corrected for the misalignment between the stock drift and the Langmuir turbulence. And we can see the small Langmuir number means the stronger Langmuir turbulence and the stronger enhancement to the upper ocean turbulence mixing. Here, you can see the spatial distribution of projected Langmuir number under each tropical cyclone. The detailed trajectory of EMFX floats is showing as light purple curves as in this figure, and the dark purple curves are the Lagrangian floats trajectory. And those small Langmuir number are on right-hand side of each tropical cyclone. This means the strong Langmuir turbulence enhancement to the vertical mixing happens on the right-hand side of the storm. And for the model setup, we set up the model with a similar way as we did for the drag coefficient estimation in the first part, but we switched the vertical layer to the 60 vertical layers, which is identical to RECO ETL 2016b. And this figure is showing the initial temperature, salinity, and potential density profile for the model simulation under for each EMFX floats. And for the drag coefficient in this part, we take advantage of the work we just did in the first part. We calculate the mean value of estimate drag coefficient in the first part, which is 0.0021, and then combine it with the GFDL hurricane drag in the low wind condition. It is shown as the red line in this figure. We call it CDM in our study. Just recall that we already know there are 3 major wave impacts. And the first one is still like the Langmuir turbulence. And the second one is air-sea momentum flux budget due to growing and decaying sea. And the third part is wave current induction, Lagrangian advection, correlate stocks, and the stock shear force. The second part, we add one more experiment compared to the first part. Experiment A is a purely wind-driven case without any wave impact. It's purely shear-driven turbulence scheme. And we use experiment A as a baseline in this part. Other experiments are as same as the experiments in the first part for the drag coefficient estimation. We just add one more wave impact step by step as we are showing in this table. So based on our knowledge, this is the first time we directly compare the observational and the 3D model parameterized vertical velocity variance at the Lagrangian floats under 5 tropical cyclones. You can view the vertical velocity variance as a turbulence level under tropical cyclone. Here I'm showing the example of the time series of vertical velocity variance at one Lagrangian float under each tropical cyclone. Different color indicates different model simulations. The blue one indicates there's no sea state dependent Langmuir turbulence enhancement. Then we can find that the model result clearly separate into 2 groups. The blue is the one without Langmuir turbulence enhancement, and the cyan, purple, and red are in another group with similar results. The result in this group is with sea state dependent Langmuir turbulence enhancement. It clearly enhances the up ocean vertical mixing, and they are more consistent with observational data set, which is black curves. And then if we combine all vertical velocity variance data under all 5 tropical cyclones and then normalized by the frictional velocity, which is a parameter enhancement we call in y-axis, and in the x-axis in this figure is a projected Langmuir number. Just recall again, the small Langmuir number means a stronger Langmuir turbulence enhancement to the vertical mixing. All data set under those 5 tropical cyclones showing as a gray symbols in this figure. Different symbols indicate different model experiments, as we just explained in the table for the different wave impact. And the green dashed line in this figure is a parameterization from Von Roy-Koh et al. 2012. Because of complex sea state under 5 tropical cyclones, our data set is very scattering. Once we do the bin average of the enhancement over the Langmuir number bin again, which is the colorful symbol, the comparison is quite consistent with previous parameterization from Von Roy-Koh et al. 2012, because the error bar interact the green dashed line in this figure. Also, the enhancement from our dataset is larger than 0.6, and the shape of the bin average dataset is reasonably consistent with Von Roy-Koh 2012. And our dataset is also consistent with the LES study near under idealized tropical cyclone in Roy-Koh et al. 2016A in the panel B I'm showing here. Generally, the observational dataset also show the enhancement increases with decreasing Langmuir number. This is consistent with both Von Roy-Koh et al. 2012 and Roy-Koh et al. 2016A. And we also noticed that there is very significant scattering even in the area study from idealized tropical cyclones. This is because of the complex sea state. So in addition to the Lagrangian flows observation, how about the EMFX float observation under those 5 tropical cyclones? In our investigation, here this is the figure of the upper ocean current vertical profile at 1 EMFX float under from Fanapi, Hurricane Francis, Hurricane Gustav, and Hurricane Ike. Here, if you focus on the model simulations, the colorful line, the model results separate into 2 groups. Extremity A and B has stronger near surface shear, and the other 3 cases with Langmuir turbulence mixing enhancement has less near surface shear. It clearly shows that the implicit Langmuir turbulence in mixing scheme and the shear only mixing scheme overestimate the near surface current shear and the current magnitude. The second group with the sea state dependent Langmuir turbulence mixing scheme is more consistent with the observational data set, the black curve, which shows the weak vertical shear in the upper ocean, and it clearly suggests that the sea state dependent Langmuir turbulence scheme is very necessary to reproduce upper ocean current under tropical cyclones. And we also want to know how the upper ocean cooling when the wind speed is larger than 25 meters per second before and after tropical cyclone passes for the all data set under 5 tropical cyclones. Here, this figure is showing the model simulated upper ocean cooling against the observational upper ocean cooling. X-axis is observational upper ocean cooling, and the y-axis is the model simulated upper ocean cooling. Different panel indicates different model experiment. The panel A is the shear only case. In the panel B, it is the implicit Langmuir turbulence mixing scheme. In experiment C, we include the explicit Langmuir turbulence mixing scheme. In experiment D, we also introduce a wave budget impact. In experiment in the panel E, we include all wave impact we just introduced. And the color indicates the time of the observational data set relatively to the time when the tropical cyclone is closest to the float array. And the red line is a fitted line for each experiment. As we can tell from the fitted linear fit for each experiment, the KPPST mixed scheme, that is the shear only mixing scheme, definitely underestimate the cooling. But when we introduce the Langmuir enhancement, no matter it is implicit or explicit, the model's simulations still underestimate the upper ocean cooling compared to the observational data set. We also noticed that the wave budget and the wave current interaction has some small impact on the upper ocean cooling, but it is very small compared to the Langmuir turbulence impact. So based on different investigation, here's our major message. We found that observed mixed layer vertical velocity variance is significantly enhanced relative to the shear only turbulence value. This is consistent with previous area studies under tropical cyclones. And the observed weak near surface current shear is consistent with simulations and with the enhanced Langmuir turbulence mixing. However, all model simulations still underestimate upper ocean cooling and the mixed layer deepening. Even the mixing scheme includes the Langmuir turbulence enhancement. This is possibly due to the deficiency of mixing scheme, which are tuned based on idealized area simulation. The missing dynamics could be the wave breaking and droplet other unresolved dynamics from previous area simulations. And also the effects from the LC momentum flux budget and the wave current interactions are very small compared to the dominant effect of Langmuir turbulence on the upper ocean cooling, but they are not trivial. So there are more details in the published paper in DGR Ocean, and that's all my presentation, and I will take any questions. Thank you all.
Yeah, can you hear me?
Yes, yes.
Yes. Yeah, thank you very much for this nice presentation. Dave Nolan has a question.
Hello, can you hear me?
Yes, yes.
Okay, yeah, this is Dave Nolan. I want to ask you more about the details of your method. As I understand it, you take parameterized wind fields and you force your ocean model, MOM6, with the parameterized wind field. You start with the GFDL drag parameterization, which bumps up and then goes back down. And then you compare, I'm trying to understand, I'm going to go back to that. There's a process where basically you, you compare to the observations to basically compare how well your results compare to the observations, and then you make a correction to the drag coefficient. Is that correct?
Yes.
Okay, but is that done? Is it you're making one correction to the drag coefficient over the whole domain? Are you doing this calculation at each point locally? I'm trying to understand like how that optimization is done.
Yeah, we do the correct calculation or correction for each data point, each observed data point.
I see. So it's one correction for every observation by an instrument.
Yes.
Okay, so there's many corrections, and then you average them together.
Yes.
Okay, but the other question is, I mean, is that an iterative process, right? Because you make a correction, you could run the model again and get a different result, or do you just do it one time?
Actually, we tried to do the simulation again, because then we apply the method again to the new simulation, which is corrected by the observation, but the drag coefficient estimation is still didn't change too much, because this method make the drag coefficient estimation is majorly based on the observed wind stress. So it just it will modify, it will return the ratio, but it won't make a big difference for the whole drag coefficient estimation.
So you're saying if you do an iterative process, like I said, you do it one more time, the results don't change anymore?
Yes.
Okay. All right. Thank you.
Thank you, Deb.
I have a quick question. If you go back to the slides where the first part, the CD scatter plot around the hurricane eyewall.
Yeah, this is the wave parameter spatial.
Yes.
Okay.
Yes. So for this one, could you explain the difference between the cross scatter and the solid circles?
That's a very good good eye. And actually, yeah, I forgot to explain that. The cross means those data point didn't pass our data quality control, and the circle means it passed our data quality control. What our data quality control means, we want to make sure the whole method is the linear terms are the major contribution to the wind stress. So once the other advection term or the pressure terms, those nonlinear terms contribute more than 20% of the whole momentum flux, we think it is those data sets are not valid for our method. So we pass it. Those cross dots means they didn't pass the linear control.
Thank you. It might be another tough question, but why are these that are not passing the quality control all scattered downwind at the track?
That's a good question because I don't know the exactly answer for which kind of dynamics control it. Just located on the far front right hand side and the front left hand side. We don't know why it is so unlinear there, but I can only tell you at this position especially the pressure terms contribute a lot to the whole momentum flux. But we don't know why. It could be a very interesting study in the future.
Thank you so much. So I see a hand raised in the Zoom by Dr. Will Drennan and another text box by Lev. So I'll let Will go first. Will, can you unmute yourself and launch the question?
Yeah, hi. Good talk. Thank you very much. So you're distinguishing between the wave age from the entire wave spectrum and the wind C here with wave age. Do you do the same thing with steepness and with direction, or are you just using the dominant, which you can see is basically the swell?
Yeah, that's a good question. We never do that from the whole spectrum because for the whole simulations, we can only for the technical issue, we can not issue. Maybe we don't have big enough storage space for the whole spectrum. So we just use a dominant wind wave direction, which is the major parameter from the WAVEWATCH III simulation. So we never do those analysis from the whole wave spectrum for each data point.
Okay, so most of the time then you're actually using the swell from the look of it, right?
Yes, that's correct. And we we had a problem about separating the swell and the local wave field because we don't know the exactly criteria, but we assume that the swell is from very long distance and it is non-breaking acid. So
it's probably from short distance and it probably is breaking.
Yes.
And that's probably why you're not seeing a significant effect on these variables, because they're really only important if you're using the local waves. Okay, thank you very much.
Okay, thank you. Thank you.
Lev, can you unmute yourself and launch the question?
Yeah, definitely. I think the first question, first off, excellent talk. I think the first question you kind of answered. I must have missed this slide, but I was just curious if you looked at things such as the wind and wave angle, which I think is what you're showing here, and how that influences the drag coefficient.
Oh, yeah.
And I guess, perfect. And then my second question, I guess, is looking at different types of observations. Have you ever considered using things such as sail-drone obs, because they have both high resolution wind and wave data in the TC. Granted, it's a time series, but there has been some work done to show that calculating the drag coefficient from that. And I thought it could be interesting because one of the things we were hypothesizing looking at our drag coefficient was there's some differences, and you can kind of explain it briefly by looking at the wind wave angle. And when that differs, that changes the drag coefficient a lot.
Yeah, that's a very good suggestion. And could you? I'm sorry, I missed the data set you just mentioned? Could you repeat that again?
Yeah, it's the sail drone data set. So the hurricane sail drone data set.
Oh, yes. We can try to investigate those wave parameter influence on the drag coefficient based on the sail drone data set. But as I remember, the sail drone data set just has a significant wave height measurement. Is that right?
So when we end up retrieving the vehicle, you end up getting multi-hertz heave data and everything that you can calculate the high res wave. It's just real time. We only get significant wave height, and there's work being done to look at getting real time wave direction, but we can calculate that post mission with the higher res stuff.
Oh, that sounds very cool. Yeah. That's a very good suggestion, and I will take a look at those data set later. Maybe we can talk a little better in the future, maybe ocean science, if I have some result. Thank you. That's a very good suggestion.
Awesome. Great talk. Thanks.
Thanks.
Lev, just to add up, I think it really depends if the sail drones were deployed into those 5 cyclones that Xiaozhui was studying. Probably they're not.
Payson, actually, there's no sail drone in those sail drone observation under my 5 tropical cyclones. So if I use those the sail drone data, I need to just target on the sail, what happened in exactly which kind of tropical cyclone. Yeah, they're totally different.
Sounds good. Any questions from our in-person audience? No? Any questions from our Zoom audience? Okay, this is your last chance. Okay, so I guess there's no more questions. So thank you again, Xiaohui, and for everyone who come in Zoom and in person. Happy weekend and happy early Thanksgiving.
Thank you all for having me. Thank you all for your time listening. And I really hope I can see you in person in the future. And thank you again. Thank you, Roland. Thank you, Payson.
Thank you very much.